Whew, transformations. Okay, so I suggest writing down everything and then starting the video over and listen to me talk. So I'm just going to go through everything, press pause, write stuff down. We're going to draw some more stuff here in a second. Press pause, press pause. Do, 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 do. You'll write this down also. We'll talk about this. These are grouping symbols, and I'm going to talk about how it doesn't matter, what grouping symbol it is. It's all going to be the same. Go ahead and write down all of this, press pause. It's not going to make sense now, which is fine. Yeah, try and draw this out as best you can. Yeah, write this down. It's a lot to write, I understand, but at the same time, it's going to make sense once I go through it. So hopefully you're pressing pause. Actually, you won't even have to start the video over because I'm going to go back and talk about everything. Pause, pause, pause. And I think we skipped these. Yeah, okay, so let's go back to the beginning. Transformations of a radical function. Well, first of all, we got all this fanciness here we're going to talk about here in a second, but here's our parent graph right here. Parent function y equals square root of x. And parent graphs are just the basic form of a certain type of graph. So like y equals mx plus b, the most basic form is just y equals x. Y equals x squared, the most basic form is just a parabola that looks kind of like that or whatever. Here is our here's our parent graph. And what all this is, H and K that you wrote down, this is my like left, right, up, down movement. Or I can have the same graph, but now it starts there instead. Or it starts over here instead. Or whatever. Your A value is going to make it to where it's potentially like wider or skinnier, just depending on that number. And a negative here will take this and flip it where it looks like that, which I can actually now get rid of. So here's the deal. This x squared graph, it should look kind of familiar because this parabola here is x squared. Well, if I wanted, I guess, to get rid of squared, kind of the opposite would be, and you can see how, like, look, if I twisted this, we get basically this graph, except we don't have this down here. Well, why not? Because we can't negative number a square root plus, I can use this line for it, this is perfect. The vertical line test says I can't touch two spots at one time, which is why my graph looks like this, because I am only touching one spot at a time. So even though these are basically the same graph, they're not. The way to get the other side, and this is why when we square root, we have positive, negative. When we get a negative version of it, then it looks like we do have the entire graph. But in reality, I'm not touching two spots of the same graph. I'm touching two graphs at the same time. Is all it is. So that's how this kind of relates to the x squared graph. So yeah, H and K, it's pretty simple. And this is what I'll kind of go here. It doesn't matter what these grouping symbols are. You have x inside something, whether it's something squared, absolute value, square root, whatever, and you have something outside. Well, I told my students just remember this pattern: left, right, up, down, positive, negative, positive, negative. And if you can't remember this order, it's how you would read a book. You read it from left to right, from top to bottom. So left, right, up, down, positive, negative, positive, negative. That tells me if I see whatever sign in here, then I know which way I'm moving. And whatever sign I see out here, I know which way I'm moving. And obviously the negative in the very front is a flip. So on this one, +2 goes left and -3 goes down. And this flips it to, well, this guy right here. I will say order of operations will say do this flip before you move up or down, because technically you don't want to move down and then flip it, flip it and it goes like way up here, because that would technically be the opposite, right? So the flip happens before you move up, down. That way you flip it at this point, then you would move it down. Also, yeah, the movement, it's a little weird. The inside is backwards. You normally think +2. Oh, I want to go +2. Well, if you think about it, right now I can't have any negative numbers. But if I take a number and add 2, well, now I could use -2 and square root 0, which is why I land on 0. That's why it's backwards. This is offsetting what can happen. This is the same. I'm going to just move it down 3. But that's why it's backwards from what you think. The cube root function is this blue one right here. There's really no restrictions on it. So you take this vertex here in the middle. Let me flip this guy back so you can kind of see what's happening. We take this vertex in the middle. This point right here is the point that we would need to move, left and down or whatever. I mean, technically, I could take anywhere where it crosses and move it left and down, but generally, this vertex point right here is the easiest point to move. So on this one, we have negative cube root of 2x. Now the 2, like I said, makes it to where it's a little bit fatter or whatever, and then we would flip it from there. So it would look something like that. But to be honest, this is where I said let's go to the calculator to see what's happening. So here we go. Okay, now I will say this is where I really showed them, like, oh, here's your cube root. If you hit number 4, here's your cube root of x. Let's type in the parent graph first, and then it wants to move it to negative cube root, so math 4, of 2x. And here's the parent graph, and here is the other graph. So we knew the flip was coming, but did this 2 really make that much of a difference? Well, if I know the negative is going to flip it, I want to see what happens if I don't flip it. Here's the parent graph, and here's the new graph, and you can tell it is just a little bit wider, which is what happens. So all you have to do on these is type in your parent graph, type in the new one, and see how, and if you can't tell because a flip happened or a movement happened, a left, right, or up, down, take those away and see what's happening. So describe the transformation of cube root of x when I go here. Well, that flips us. That goes down. We don't have to really draw anything. Domain and range, we talked how, well, like on square root, we can't square root a negative number. And when we square root, unless we have the minus there, we're not going to get a positive number. We're not going to get anything down here. So domain is all the x values I can have. And here I can start at 0, which is why this is a bracket, and I can go as far to the right as I want. So I'm going to infinity with a parentheses. We would use parentheses with infinity because there's no stopping point. You would, if there was a stopping point, then you put the bracket. Range is the same way. I can't go down any, but I can go up forever, even though it's not going very fast. But domain and range change as you move left, right, up, down, because now my domain can start at -2 and go forever. In my range, I can actually start at -3 and go up. So how you move your graph tells you domain and range. Now, move you out of the way. Cube root is a little bit different because we can go all the way to the right, all the way to the left. It doesn't care about negatives or whatever. So my domain is actually all real numbers, or negative infinity to positive infinity. Range is the same way because this goes up forever, this goes down forever. Even if we flip it, that will go left forever and up, and that will go down forever and right. So cube roots have all real numbers for domain and range. It's not like the square root of x where you have some sort of restriction. So graph this and identify domain and range. Well, when we move to the left one, then I didn't move up or down, so my range stays the same, but now my domain can start at -1. Describe the transformation. Well, inside minus, because remember it's left, right, up, down, positive, negative, positive, negative. Inside minus, I'm going right 3 units. Outside plus, I'm going up 4 units. This is, I'm going to flip, and that negative means I'm going to flip something, and that means I'm going to get a little bit wider. And you just go to your calculator to figure that out. But I will say, if this is a number larger than 1, it's going to get wider. If it is some sort of fraction that is less than 1, it's going to get narrower. And they talk about like horizontal compression and vertical stretching, and we're not going to get too complicated. Just tell me if it gets wider or narrow. That's fine. So these should start to make a little more sense. You wrote these down already. And here, again, domain and range. Domain and range, this one, we didn't move up, down, left, right, or all. This one just got skinnier or narrower. This one, cube root, means we're going to have all domain and range anyway. So graph this one and identify domain and range. So we moved to the left one, and our domain went backwards 1. So on a number line, if we're moving to the left, knowing that my graph is going to start like this and go that way, if I move to the left 1, then I know my domain goes backwards 1. Describe the transformation. Well, we flip, and then because that's outside my square root or my cube root, I know I'm going down. So that was pretty much it. I know this one's a little bit weird, but you got a calculator that should help you kind of figure out. Just put in the parent graph first, the most basic form of square root x or cube root x or whatever. Then put in the new one and just kind of see